right, it's probably enough to get started. So for anyone who hasn't come before, we are Rust and C++ Cardiff. We've got quite a few organisers. So myself and Krzysztof and Chris, who is CJ, will organise it. And we've got Dan as well, but he's not here right now because life is mad at the minute. But happy St David's Day as well from Wales. Dydd Gŵyl Dewi Hapus for any Welsh here. We have a Twitter and an email address. So if anyone is interested in speaking, please feel free to drop us an email or tweet at us because we're always looking for more speakers. And our objectives as a community are just to mostly learn and share and get excited about Rust and C++ and learn from each other. And Esri sponsors us, so that's who me and Chris work for. And they organise the actual meetup page, which is super helpful for us to do this. We have a code of conduct, which is generally just following the Rust code of conduct, but the overarching vibe is just be nice to each other, which I think most people are. So everyone we've interacted with anyway, we'll may that continue. We have a Pac-Man rule for physical meetups, which is just generally when you're kind of chatting at lunchtimes or in between, just leave a space so that anyone who's new can just come and chat. It's always a bit intimidating, but in a virtual meetup, obviously it's a bit more casual and people can just unmute if they want. You don't have to. It's nice to have anyone be able to come along. So with that, I'll probably hand over to Krzysztof if you're ready to go.
Yeah, I'm just making some finishes. All right. So can you see my screen? And by screen, I'm also saying like the command line.
Yes, we can see your screen.
All right, awesome. Cool, so we can start digging a little bit into WASM, right? So the presentation is going to be about the WASM, and that's been a funny journey for me because I haven't done WASM before at all until preparing for that presentation. I've been reading a lot about it, but never touched it really. And that occurred to be a challenge, but also like a very interesting challenge. So this is going to be presentation, but also is going to be a demonstration about the process of modifying a native application. So quickly, we'll have a look at what is WASM, and then a little bit we'll peek into the memory model for a WASM, and with some code examples. And then I'll tell you about the demo application I tried to create for this presentation. And meaning we'll start with the native application, then try to extract some shared code base between the native and the WASM, and then run the other counterpart in the browser. All right, so I haven't read a spec for WASM, so what I'm telling you is just my perception of WASM, right? And WASM basically for me is just a runtime, and it's a runtime which describes what kind of binaries it takes. So it specifies the bytecode, and it says basically that, oh, I'm a virtual stack-based machine, and please provide me with the code in a particular format, right? And then once it gets that code for that bytecode, it just recompiles it to native code, and then it tries to instantiate it with whatever the runtime provides for that code. And in such scenario, it works this runtime works as a linker. So basically, when it recompiles the code, then it figures out what the code needs from the external stuff, and then it provides it if it can. If it cannot, it just says, oh, I cannot run this code. And what is very interesting is that there are many runtimes for the WASM. So you might have browsers runtimes, and basically most of the major browsers are compatible with WASM right now. Then you can have backend servers where you could run WASM, and that's like Node or Deno or probably whatever else there is. You can have some specific WASM runtimes like WASMer, and there are a lot of them. But also what is interesting is that there are lots of embeddable runtimes. So you can, for instance, write your C++ code, get the library with the runtime, WASM runtime, and then you can load runtime plugins, you could say, into your application so that the plugin itself is cooperating with the application. So there is lots of, basically, lots of potential for that technology. And why we would be thinking about WASM, I guess, is that it just has a potential to become a the standard, right? And the standard for the universal binaries that are basically running very quick, because they have to still be converted to the native code from the that WASM compliant binary, but it's basically done once. It's not very expensive process because it's already represented as the some virtual machine, and then yeah, then basically it allows to run those binaries almost with the native runtime, but you can run it basically on like probably most of the computers that you can think of right now. And yeah, there are people saying that it might be a Docker replacement, right? So with the proper WASM runtime, you basically can do with that WASM binary whatever you would want to do with Docker. And I think the creator of Docker said at some point that if in 2011 there was WASM already available, then you would be able, or they wouldn't come up with the Docker. I might be making that up right now, but I read it somewhere, I think. Yes, so quickly, what the WASM is that you take some code of C, C++, Rust. There are other languages like Go. So there is Go support, but not for the full Go, but Go embedded. I think some Java, C#, and so on. They are all compilable to WASM, right? And there is some problem with some external languages because, or with some other languages. So this is the main. These are the main three languages that are working very well with WASM. But the other languages, especially the ones that are garbage collected, so they have a problem that they have a full bloated runtime, and then that runtime has to be also compiled into the WASM binary, and then the runtime of that application has to work properly with the runtime of the WASM itself. So there are just challenges, but it is basically possible. But yeah, what WASM is or the way how WASM works is that you have a compiler that compiles C, C++, Rust to the internal representation, and then spits it out as the binary in form of WASM. And then the browser basically is converting that WASM to whatever native platform is taking, right? So you have a front end taking, for instance, C code, then you have the IR representation that converts it to some WASM representation. It's not Clang IR representation, but it's WASM representation, and that was a deliberate choice. And then so this is how you deliver it to, for instance, to the browser. And then once browser is getting the WASM, it does its own compilation to the native code. I stole these images from there is a lady working for Mozilla, and that was WebAssembly cartoon explanation or something like it. And so basically how WASM, especially in the browser, works is that the browser obviously has some memory, right? And it can allocate a contiguous memory for the WASM binary to run into. And then when the WASM binary comes, it says, oh, hey, browser, can you give me some memory? So memory is given that, so the browser is giving that chunk of memory to the WASM binary, and the WASM binary can only write to that one, to that part of the memory. It cannot write to any other part, so it's sandboxed. I didn't mention that it is sandboxed, in fact. And this is basically how WASM can cooperate at the moment with the WASM runtime. It's only via that particular memory that is getting during the instantiation. Yeah, and then WASM basically using only integers at the moment is just saying, hey, I filled in the memory that you gave me. I filled in it at particular address. Here's the address. Do something with it, and then the runtime, for instance, the browser would just try to read the memory, and then it would interpret what that memory is, because it potentially knows what the memory is representing. So it decodes the bytes in the memory into whatever the representation. So it is serialization and deserialization, basically, for communication purposes. And then it can read. Yeah, so I did mention that, but WASM is all about security as well. So it's like WASM in its entirety is not talking at all to the operating system, but it's first talking to the runtime, and then runtime can sandbox it and protect it from particular actions or forbid it from particular actions. And also it holds for the memory. So if it's giving it the memory, it only the runtime is checking that WASM binary can only access that particular chunk of memory. So it is giving you lots of safeties, right? And if the WASM runtime, for instance, is trying to access some outside of the memory that it is forbidden, it's gonna be probably killed. That's what's happening basically on the browser. Yeah, so that was a quick information what the WASM is, and I'm trying to speed it up a little bit because there is lots of to be shown on the second part, and the second part is basically a demo application, right? So yeah, it's hard to tell if the technology is mature enough, if the technology works for you, and if you could use that technology maybe for your production for the production without really trying it. So that's what I did basically with WASM recently, and I just tried thinking about the application. That first I'll write in C++, and then we'll try to get part of that code and reuse it in the WASM environment. And I've been trying to do it in like in a way how I would do it probably at work, so with the proper build system. And I didn't introduce the CI because that would be too much, but it should be all controlled at least by the build system, and then once I know that I can run commands to build it, to run it, and so on, then it would be nice. It would be easy to automate all of it, right? Yeah, so I thought about the application that should be doing something simple but complicated enough to be able to use multiple libraries, have some external word access, and so on. And basically I thought about a simple application for file compression, and I found out some library on GitHub, which was mean-z, and basically I'm using that library to compress a file which is on the input, and then I'm speeding it up to the output, file input, file output, right? And then I first wrote it on the command line, and then I tried to convert it to the browser form, which basically allows you to drag and drop a file that needs to be compressed, and then it so the application in the browser would compress it, and then it would tell you to download that file. On the browser, I didn't do decompression because there is more complication on the decompression, but at least it's like this application is already giving me, and hopefully you, some kind of information what it involves to get WASM working. Yeah, and so I didn't mention that, but I did it in C++, and I think Rust toolchains and everything is prepared now better for working with WASM. So whatever pains I have, for instance, with CMake or whatever, it should be much easier to work with Rust. Yeah, so that is the goal, and I'll show you how that application looks like. and basically this is the application, right? So I take some file. So for instance, I take a test file that has some text in it, and then I can drag that file and download it as a compressed file. Yeah, and then the compressed file is basically full of garbage, but it can be decompressed with the command line. And I'll show you that later. So let's have a look how I did try to approach it. But first of all, I want to show you how or what it takes for the WASM to be, or what it takes to work with WASM, right? And I said that I'm gonna be using CMake for compilation with the full toolchain and so on. But let's have a quick go at what it takes to compile simple WASM application, not Rust.
Just a heads up, Krzysztof, the font's maybe a little bit small if you want us to read any of that.
Oh, all right, yeah, on SmartGit, I probably don't know how to increase that font, probably with the system, but that shouldn't be a problem. I'm just gonna be traversing the history of the project. I'll increase the font size on the command line, right? But basically, yeah, basically, I want to show you what it takes to compile something into Rust in the simplest scenario possible, right? So if you have a look, I have a main code, and basically this is the main CPP file that has a code in it, and it's just defining an int function, taking 2 ints and summing those ints out, right? I did so usually using WASM, you would be exporting the functions as externc, so it doesn't do the signature, the name mangling so heavily, just with the underscore as a prefix. Yeah, and basically, let's say you want to use such an application, or you want to create such a WASM module, and then load it in the browser and use it. So what you would normally do is you would take your tool chain and run such a command. So you would basically take some new Clang C++. You would say, hey, the target I'm targeting is just WASM 32. So this is what we've been saying. The WASM is basically a specification of the virtual machine that has some particular ABI requirements, right? And you would be saying also, oh, I don't want to any standard libraries because I don't have any standard libraries for that particular target, but I want to export all because I want to export all the symbols available in that code, and I want to output it as a WASM binary, right? So I need to have a particular Clang that supports it, and what I did basically is I downloaded mscripten Docker image, and that not only has mscripten in it, I'll tell you what the mscripten is, but it also has the newer version of the Clang in it. So I'm gonna be using that one, and just to show you what my alias doc emcc bash is doing, is just saying that get me the image of emcmake, mscripten cmake, run bash command in it, and then mount a current directory into the source directory and use some user IDs and the group IDs, and that's just so that when it produces the files, it doesn't write them as root or whatever, right? Yeah, and basically, and for future, I'll show you. So I'm also forwarding ports on that Docker image. But basically, what you want to see, or what you need to know right now, is just it's basically running the Clang command that we just had a look at inside that Docker container, and it's gonna be creating that add WASM into this local directory. So you can see that I've been committing also binaries, but I did it for a reason, right? It's not that I'm stupid and just adding everything to Git. Right, so yeah, so let's run this code. Docker requires root permissions. It produced the add WASM, and if you have a look, it's just binary, right? So it's a binary with some symbols, and basically that is like the code, and then there is a text section. But what is really worth thinking about the WASM code is just the file format, like Windows file format, PFE or whatever they call it, or dwarf on Linux or Mac on OS X, right? So there is a file format to be interpreted by the runtime environment, and then inside that file format you will have some part of the code section, right? And if so this is the binary, and that's what all the runtimes are taking, or probably most of the runtimes are taking. But if you want to have a look at what is inside such a binary, there is a wasm to what command in wasm tools repositories, and basically it can spit out this particular binary into some user-friendly or human-friendly format, which is called S expressions. And this is like an assembly language for creating yeah, this is the assembly language, and then you can, if you wrote it by hand, you could compile it back to the WASM binary. And again, this is a file format, right? So basically what that particular one is saying basically is that it's saying, for instance, there is a function with the code doing something specified with particular instructions, right? And there are global variables. Yeah, there are some. This, in fact, is not saying the global variables, but it's, for instance, saying there is gonna be a memory variable, and me as a binary. It's saying I'm gonna be exporting particular symbols that the runtime can take a look into, or yeah, take a look into. So this is by the export keyword, right? If there were imports, it would basically be meaning that this binary needs those imports to be instantiated by the runtime for it to run, right? Yeah, and if you want to have a look at how such a binary can be run inside the browser, you basically create a quick or short index file. And what the browsers are doing is that in the scripts section, you would basically say, hey, browser, I want to get the add WASM binary from the same location that I just got index.html, right? Then after that has been fetched by the browser to the client, then it's basically converting that to bytes, so in-memory bytes, and then it's compiling it and instantiating into something called into WebAssembly instance, right? And that instance, once you did manage to get hold of that, that means your code has been compiled and it can be run. There might be bugs, but it can be run. And if you remember, we have exported the add function, right? So what you would normally do is you would just say, on that instance, there are gonna be exports, and inside the exports you have add symbol, and you know from that assembly code that the add symbol is pointing to the add function, right? And the add function is taking two integers and returning a third integer, or in fact, it's written here. but it's also saying type 1, so that's why I pointed there. So let's have a quick look how it works. And the best option is just to have a running web server. Python is doing that. HTTP server, and let's put it on port 8000. So if you have a look on the command line, we just put out the answer is 3, and this is basically what our code did, right? So if I reload it, we have a breakpoint, and you can see that the instance of our code has been instantiated, and this instance has exports, and on the exports you have add, and you have a memory, right? And this is exactly what we've seen here and there. It's funny. Yeah, and you have those underscore stuff as well. And this is stuff that's been just created by the compiler. I did mention on the slides that currently WASM is basically can communicate with its environment as with integers only, and the memory, and obviously the pointer into memory is the integer, and serialization, deserialization has to be done by yourself. So this was easy to use because we were using integers, right? But if we want to use something more complicated, then there would be complications. And let me just show you those complications. So right now on the main, is it better? All right, so that was our previous function, and right now on our we just created a new function, and we said that this function is gonna be doing memcopy, and the first argument is gonna be in, then size and the out, right? It's not how memcopy has its declaration. I'm aware of that. And what we're just doing is we're doing the for loop, and in the for loop we're just stupidly copying one from one to the other, right? Compilation would be the same, so run, it would be the same. We're not getting the standard libraries, we're getting main and using the WASM, or outputting as add WASM. There is a modification now to our index page. Maybe that was a little bit too big. And so previously we finished here, right? But now if we wanted to did work with the memory and share the memory between the JavaScript and our C++ code, then what you would have to do is, so let's say the goal of this code is basically to get one array, and then using C++ and WASM runtime to copy bytes of that array into the other array and get and check that the array has the bytes set, right? So how you would do it with WASM, or first in JavaScript, you would create an array with some prefilled data, right? And this is the way of just doing iota on the array. So I created an array of uint 8 array of 10 size, and then said each element should have its index associated with it, so it's from 0 to 9. Then now we're using a memory symbol from our WASM instance, and memory symbol is basically like a memory. On our slides we saw that the runtime has allocated some memory to WASM binary, and this is basically that memory. So in that memory there are different sections used by the C++ runtime, right? So runtime, I think it has some stack associated with it, and obviously it has some heap associated with it. The pointer to that heap, again, has been exported by the C++ runtime for us using the -- heap base symbol. So basically what you're saying is that if I don't want to screw anything with the C++ code, so if I don't want to, for instance, override stack or some global variables or whatnot, then I probably want to work inside the heap. And we know it's safe now because we're not doing any allocations in our code. So basically all the heap is available to us. So what you would be doing basically is that you would poke into a memory available, shared between the JavaScript and the C++ code. You would move to the offset of the heap in that memory. So we're basically saying we're not going to be starting at the heap start. We're going to be starting at the heap start +2. So that's our chosen source start. And then we're copying our JavaScript byte array contents into that particular place, the chosen source start of the shared memory and the heap chunk of the WASM C++ code. And then if we want to copy it over, we still have to copy it. If we're doing that from the C++, we still have to be copying it to some part of memory that is available to C++. So again, that's going to be in the heap. And if we want to do it to the heap, we want to make sure that we're not overwriting our source array. So we're just going to be copying it from to the destination that belongs to the chosen source array start. We shift it by 10, and then for whatever sake, we also add some 5s. And basically these are the pointers that we're going to be giving to the WASM, saying, hey, this is our char array source char array pointer. This is our destination pointer. And this stuff is just so that we can print out some more information about, or from the JavaScript code, we can print information about the destination chunk of that heap memory. So first here we should see that it was all filled with zeros. And then when we call unsafe memcopy with our source array pointer, the byte length or the byte length of the source array and then destination source array pointer, we should see that it was prefilled, right? So that would be basically checking if our code is working.
Yeah, time check, Krzysztof. We're just after 7. Yeah.
Oh, okay. So I will have to speed it up then. All right, so you can see what the same code has been run basically, right? And then if we do Python and serve it, then you would be able to see that we have run to the same code, and we see that it was 3. And now stepping one by one. First of all, the destination array is filled with zeros. We call our C++ code, and now the destination array should be filled with 0, 1, 2, 3, and so on. When we are printing it, we moved our pointer for printing outside by 2, so that we are sure that nothing has been like changed in the vicinity of it, right? So we have, but it hasn't, and we can see that it's been that from 0 to 9 copied over. Okay, shit. So I'll move to basically to the project. And I can open the project in the Qt creator. How do we increase that size here? All right, I'm stupid, sorry. So I'll. So the project is simple. It's but it's using something called CPM CMake package manager for getting particular libraries. And what this project is doing, sorry, what this project is doing is just so it has a CMake project, main CMake project, and it's are in the source directory, and in the source directory we again are using the package manager, and we're using the format library, the mini Z library that I told you about. That's the application. We're also using some argparse and the Google test, and we're gonna be basically using few files, compressor and main CPP. I'll show you what those are. So what the compressor is doing is just a class, but it's stateless class, so it didn't have to be really a class. But what it's doing, it's just compressing the input array by size of something to the output array of size outsize. And it's using that min-z library. And we're just basically saying, so we're delegating inside that function, we're just delegating to the other function. And we should get the compression just by calling that library, right? It can fail if the output buffer is not enough, or it can fail in, yeah, probably only if the output buffer is not enough, right? So that would be our compression. And then we also want to specify some decompression, also providing char array size, and then char array pointer to the output buffer and the size of the output buffer. And this is more tricky because it's easy to say that when you're compressing, it's easy to say, if I'm having a size, input size of something, what the output size should be, or at most will be. But on the decompression, like the algorithm can probably squeeze from it can compress into 10 bytes, for instance, something that is 1 meg, and it's not, we're not able to say it before we really start decompression. And I wanted to keep it simple, so I'm using such, I'm basically saying, when we're decompressing, I'm going to be providing a byte buffer of the size 2 times the input buffer. So on the calling code, but that is a bug, and that sometimes may fail. So you will be able to see it later on. The way how we work is that with the native application, that's a command line application, and we specify just the command, the input, output file, and then once we get those, depending on what the command is, we're doing some basic checks. And then if we're saying it's been a compression, then we say, so we get the data from our input file into in-data stud vector, and then we allocated out data with appropriately sized buffer. So we're compressing from stud vector to the stud vector, and then we're writing that output stud vector to the file that was requested by the command line. But when we're uncompressing, as I said, to that 2 times size of the input buffer, and that sometimes might not be enough. Yeah, so I did mention I varied some of the tests as well. So if we look into the test directory, you're going to be able to see that we have 5 tests or 6 tests that basically are saying that if the parameters are wrong, then the compression should fail. If the output buffer is too small, then the compression should fail. If there are sensible parameters, compression should succeed. But if there are sensible parameters and the compression should, and the compression is not, so when we have some text buffer, we're gonna be, oh man. basically these are just tests, right? And those tests are working fine. If we have a so this would be a project basically that we're going out from, right? And now we want to convert it to the project that is consuming WASM. So first, what we would do first of all is that we would basically try to move the compression logic to the separate directory. So we would create directory source shared and move the compressor to the source shared and the compressor header to the include shared. Then we would create a CMake list for that particular shared directory in which we would be creating so I'll show you. In which we would be creating library, and this particular library is only dependent on the FMT and minz, and we are creating the WASM demo library. But from now on, our production command line logic would be dependent on that library. So not only on the FMT argparse and on the Google test, but you would be able to see that it's also dependent on the WASM demo library. So both tests and the native application. And then when we, so that would be the first step. And going to the second step would be to add some logic needed for WASM. And the WASM logic would be basically again, a CMake project saying that, oh, I'm going to be using the WASM demo library when I am build against WASM target. But you need to also add some, so this is using mscripten, and mscripten is expecting you to say which functions should be exported into the WASM binary. So we want to export main to get the initial logic in, and then demo compress, demo decompress, and the demo max compress size, because we're going to be using them. And if you have a look also on the shared logic, we've added some externcies for the same reason that we've seen on the main C++ in the in that simple compilation step. So basically, we can use C++ code, but we need to wrap it up into C, saying that again we're going to be using just buffers and then compressing it with our C++ class compressor, decompressing it with it, and then asking our library for the maximum compressed size.
The time check, Krzysztof, we're coming up to the end, just to warn you.
Yeah, so you know what? I'll just, yeah, that wasn't the best shot, in fact. Shit. So I'll basically show you how all of that can be built for two architectures, right? So sorry for me taking lots of time. Native. So if we're building something natively, it's just normal stuff, right? So we basically say CMake configure yeah. So this is just I just want to show you that this project is capable of building for WASM target and for yeah. obviously, when building for different architectures, you have some code dependencies. So those code dependencies I hide with CMake by specifying the flags, right, for native or for WASM. So when building for native, I'm using that flag, and then it's using one native directory. If compiling for WASM, I'm using for WASM flag, and then it's compiling. So this is just compilation for our native application of the same project. If you wanted to run some tests, the tests would be run. Don't worry about the output. That was just a helping output, but 5 successful tests. And this is our application, right? And then if we wanted to run it for WASM, we would basically do the same. I'll do that. Just a helper. So what we're saying here is that we are running CMake, and we're building for WASM with some debugging flags, right? But we're using mcmake wrapper. So this is from our toolchain mscripten to set up proper flags for CMake. It's configuring the project, and now the build works just normally. As for the other projects.
While that's building, we had a question. Is there any good reason to use C++ over Rust for new WASM projects?
So the good reason is that, like, for this demo application, what I try to be doing is that you have a base application in C++, and then you try to not rewrite everything, but reuse chunks of code to get the the WASM application, right? And this is something I'm thinking on our at work to do at work. So we're doing the file compression and so on, or not file compression, file encryption, and some of that currently we are using native applications, but with the same logic and with the same code base, we potentially could spare our clients from installing native applications and just go to the browser and use WASM to encrypt the files. So instead of me rewriting everything in Rust, which has its challenges because at my work, no one really knows Rust, not that I know it much, but I probably know the most of it at our workplace. Yeah, so basically that is just code reusal, right? So when you're building the code with WASM mscript, and not only you end up with WASM, but you also end up with the WASM demo WASM or with the JS file that you should include into your index HTML or whatever your HTML web page is, and that does lots of the setup for you. So if you have a look, yeah, I wanted to show you that. So what I want to show you is that this WASM binary that I just generated, I will be able to open it in the Node project, and the Node project is running tests in Mocha, right? So you can also do unit testing using that C++ generated WASM in your JavaScript environment to be able to see that it does work. The comments. I did install it, right? So I'm just copying the artifacts from the other build directory, and then I'm just saying, hey npm, run the tests, and you can see that there are 5 tests. Some of them are expecting the failure, right? The last one is expecting the compression and decompression working, and yeah. So that's kind of production kind of automation, because you basically want to have unit tests, right, when you're building your production code. And then if you want to integrate it to your when you want to integrate it to your web page, what you're doing is you're basically using yeah. I'll change my password. Yeah, what I wanted to show you also is that after all this has been built and the artifacts have been copied, when we're trying the function, or when we're trying, what we need to do to get it into the browser. So we know that now it works in the Node ecosystem, which is basically a browser without a view. Then what you're doing is that you're including the mscript generated file, you're including your JavaScript file, and in our case, what we're doing is that we are having the file input, and when you specify the input on the file, the browser is making that file available to the JavaScript engine, so you can start reading the file, converting it to byte array, and then once you have a byte array, we're just calling the compress function that is calling our JavaScript function decompress.js. And if you have a look what this one is doing, it's basically so we have a data from our file to be read, or it's already available, it's in the byte buffer, and then what we're doing is just using unscripted module. We're calling our C++ function _demo compress with our input buffer and with our output buffer, and the C++ code is doing that encryption, and once encryption finishes, that code being run synchronously would finish, and you would end up with the encrypted, with the not encrypted, with the compressed code. And once we have compressed the code and we have it as the compressed output data, we just would create an Anchor element in HTML in the DOM, and we would just call the download. Yeah, that's been. So sorry for rushing, sorry for not showing everything, but basically, all in all, it is working, right? I will push that. So I have already pushed that code into the GitHub repository. You can have a look at it. I did show you some debugging, but I did show you the debugging just on the JavaScript, right? There is an option of debugging also into the C++ code, or at least seeing which parts of the C++ code are being executed. But the limitation is there that you cannot see the variables, for instance, which is really, really problematic. So you do have to have tests, and with the tests, you just do your investigation spikes. You cannot really do investigation spikes in the browser yet. There are memory constraints, so I haven't shown you that. But for instance, if I wanted to, is it running? It's not running. So if I wanted to compress some bigger code, did I? Okay, so I'm not gonna be showing you that. I don't know why I didn't start now. It's already past the time. But basically, when your runtime is giving you memory, right? It's the limit of the memory, and you've seen in the code I've provided. It's simple code. So basically, we're reading the whole file into the memory. Then we're creating a buffer to hold that file, but the buffer which is shared within with the WASM binary, and then we create at least two times the buffer for the output, right? So that if you're dropping a file of few tens of megs, that would end up as few hundreds megs of code, and you have to be aware of it because your WASM is going to be limited. And if it's not going to be limited, and if you allow explicitly for it to grow the heap, then it's you might basically have some more problems with it, because whenever there is a growing of the heap, you reinvalidate all the views in the JavaScript side for your memory, and there are problems to be expected, I guess. Yeah, the good thing is that you are really forced to recompile everything, and that's also what DM scripting is doing. They have Mosel libc that they're recompiling for you, and then they're hooking in basically where the system calls would be, and then they are redirecting them to the JavaScript code to be executed inside the JavaScript, because there is no operating system, it's all in the sandbox. Yeah.
Awesome.
Thank you for listening. Sorry if that was a little bit or a lot. Yeah, if that wasn't the best presentation.
What we can do as well is at the end, if we come back for questions, if there's any little bits that you didn't get a chance to show there, then you can always pull them up at the end. And
all right. Yeah, in fact, there was a lot. I imagined to be quicker and not. Yeah.
No, that's super interesting.
It's really fun to play with WASM. But so my next step is really to now, as I know how to do it in C++, is not fixing the code from those little bugs, but now to move to Rust and see how much easier it's gonna be in Rust. Yeah, I think Rust is now the first-class citizen for if it comes to WebAssembly. And even though it started with C++, the Rust has better experience from what I read.
Speaking of, we shall now be switching over to Jason White to talk to us a little bit about Rust and building a Git LFS server.
Sure, just let me, yeah, I'm going to share my screen. Okay, can everybody see that?
Yeah.
Cool. Okay, today I'm just talking about my experience building a Git LFS server with Rust. So first of all, what is Git LFS? It's a Git extension for versioning large files. LFS stands for large file storage. Basically, instead of storing like a big binary blob in the Git history, you store a SHA-256 hash instead, which points to some content addressable stored somewhere else on a different server. And when you do git checkout, all that data is downloaded, but you don't get any of the history of that data, only if you check out an older version. And this is often used for game development or software applications with many binary assets. So why would I write my own Git LFS server? There are 28 existing Git LFS server implementations available, but about half of them are probably outdated. They don't support the latest protocol, or they have some other issues. So the main one is GitHub's own LFS server, but it has storage and bandwidth limitations. If you go over their limits, you have to start paying. Some of the other enterprise solutions are slow and expensive. For example, Artifactory. There's another one called Nexus. Those are written in Java, so they're slow by default. Another problem is they don't encrypt your data. So if you want to do cloud storage, that's not going to be encrypted. If maybe you have some like government contract that requires you to encrypt your LFS objects while they're if they're sitting on someone else's servers. Another issue is if you're using cloud storage, there's no local caching of the LFS objects. So that's really nice if you want to avoid hitting the cloud storage service if you don't have to. That could save you a bundle of money. Yeah, so some of the naive implementations of Git LFS servers will when you upload a object, it might load up the entire object into memory. And if you say upload a very large object, you could get Linux to kill your process because it runs out of memory. So I think all these issues could be solved. So I wrote this project called Rudolph's about 3 years ago while I was working at Esri. I no longer work there, but as far as I know, it's still being used. Maybe some of the people here could chime in on that. I think Craig Williams is here. Maybe he can speak to that. So it decided to use Rust for its speed and safety. Took about a month to get it 95% working, another month to finish the last 5%, just iron out some bugs and stuff. It's open source if you want to check it out. It's this URL. I don't spend that much time nowadays maintaining it. For production data to go away. And I also wanted local disk storage to cache downloads from cloud storage to reduce your Amazon S3 bill. I wanted streaming uploads and downloads, so in other words, don't accumulate blobs into memory and blow up your machine. Sorry, somebody mind muting? Okay. Encryption. I wanted encryption for that, just for an extra level of safety. Amazon S3 has this option to automatically encrypt your data, but I imagine they store the encryption key on their servers, which kind of defeats the point. So I want it to be faster or just as fast as the competition. And since the competition is mostly written in Go and Java, I think that was not that hard to do. So let's look at some dependencies that we might need for this project. First of all, we're going to need a HTTP server. So we use Hyper for that. We're going to need to be able to serialize and deserialize JSON for the request and response payloads. The entire LFS API is JSON based, so Serde is really nice for that if anybody's used it. We also need a way to communicate with S3. So there's this project called Risotto, which basically covers the entire AWS API. It's quite extensive. I think they do a lot of code generation to cover everything. We also need a linked hash map to for LRU cache. least recently used cache. So we're going to only keep the most recently used LFS object in our cache. So if something's old and it's not used ever again, we don't need to keep that in our cache. We also need to be able to hash our objects as they stream in and out. So we use the SHA-2 library for that. And also Cha-Cha for encryption. Cha-Cha is a stream cipher encryption library. So you can do encryption as your object is streaming in. You don't need to keep the entire thing in memory. So let's look at the architecture for this. Let me get my my pointer here. So I hope everybody can see the red dot. Hopefully nobody's cat is around them. So here the request comes in, streams through the LFS server API. It's basically where routing takes place, kind of based upon it's a REST API, so it decides where to route the request. So a request could be something like download this object or upload this object or tell me if these objects exist yet or not. So request comes in, then we route that to our storage backend. So this whole stack is our storage layers. So as say we do a upload request and we want to upload an object. Say that object is 4 GB in size. As we upload that, we want to verify that SHA-256 is valid. And as we do that, we pass it through the encryption layer, which encrypts everything. So after the object gets through this layer, it's encrypted. And the caching backend just deals with the encrypted object. And the caching backend will decide whether it wants to upload to S3 or if it's already in S3, just or if it's on the disk cache, just don't do anything. It doesn't even need to talk to S3. So yeah, so then the response goes back through these layers and back to the client. For a GET request, if we want to get an object, same thing, goes through here, but since we're not uploading anything, the verification doesn't happen on the request, it happens on the response. So, and same thing with encryption. When we get an object, it doesn't happen on the request, it happens on the response. So we go back through here, caching backend looks to see if the object is in the cache or not. If it's not, it'll hit the S3 backend, and then it'll stream the object back through these layers. So since remember that the object is encrypted while it's sitting on either the S3 backend or the disk backend. So as it passes through the encryption layer, it gets decrypted. The SHA-256 gets verified again. Maybe while the object was sitting in our cache, some bits were fiddled with. Maybe a cosmic ray came through and looked a bit and changed the hash. So we're going to verify that, and I'll talk a little bit about that later on what to do in that case. And so the response goes back through to the client. All right. So let's look at how we implement this in Rust. We've got this trait. It's an async trait. This is a proc macro. Normally you can't use async with traits. What this macro does is just transforms it in such a way that it makes these methods async. So we have just a couple methods here. In reality, there's actually more. There's, say, one to delete an object or one to list out all the objects that sit on the back end. So when we get an object, we need a key. This is basically a key value store. So we have a key. The key looks like this. It's a namespace plus an object ID. The namespace is basically just the org/project. So if you're looking at like github.com, you have the organization / the project. It's just a way to kind of separate different projects. So if you ever need to do some manual maintenance, you can go into Amazon S3 and delete the entire subdirectory instead of trying to sort out which objects belong to which projects. And the OID is just a strong type for the SHA-256. So that's what the storage key is, and then we get back a result of an option of an LFS object. I don't know what people's experience is with Rust, like on what level it's at, but so I won't explain what a resultant option is. Hopefully that's obvious. So an LFS object is a length and a byte stream. And this byte stream is it's a stream of futures, so they may not be there yet. We have to pull the stream to get back the bytes. So that's a box of a stream where each item is a result of bytes. So bytes is just it's basically a reference counted vector of bytes. So actually, this LFS object type is only, let's see, 8 bytes plus 8 bytes for the box, so it's only 16 bytes total. So that's a GET request, PUT request, basically the opposite. You give it a key and you give it a byte stream, and that gets uploaded into the storage backend. So let's look at these different layers and how they're composed together. It's probably easiest to read this from the bottom up. So we run the server with a storage backend. This type will implement this trait here, the storage trait. So working backwards, we have the verification layer, and we pass it the encryption layer. So when we have a request for the storage, the verification layer handles that first and forwards that request on to the encryption layer. And likewise here, encryption layer forwards that request onto the caching layer. After it does its thing, it might modify the byte stream. So like this will transform the byte stream, to decrypt it or encrypt it, depending on the request. And that passes it on to the cache. And the cache takes 2 storage backends. So this is awesome composability at work. So the disk is the local volatile cache, and S3 is the permanent storage backend. So that the order of the parameters is important. So disk backend, we use that as our cache. Basically just stores LFS objects locally. And S3, of course, you store that in some bucket somewhere in the cloud. Okay, and yeah, we give it a socket address and that starts our server. So let's talk a little bit about the caching layer here. So the uploads and downloads are always streaming, as you saw in the byte stream object. There's no buffering ever. So we don't accumulate huge objects up into memory. So everything's pretty fast. Everything kind of just streams through the system. Doesn't need to accumulate tons of data. And we only talk to S3 if the local disk doesn't have local disk cache doesn't have the object that we are interested in. And when we upload an object, they're streamed to disk and S3 simultaneously. So I'll talk a little bit about that more. Basically, we split the stream, and I'll show you a code example about that later. So the caching problem, I worked on this kind of probably one of the hardest parts about implementing this whole thing, just because of the streaming nature. So the problem is we might cache failed uploads if we're sending this byte stream to both S3 and disk simultaneously. So if the upload finishes, say it's a small upload, a small file, and we only need like one packet to get that sent to S3. S3 might respond with a HTTP failure saying, hey, you can't do that. But then the disk will be fine. It'll stream to the disk just fine, and it'll go into our cache. That'd be bad because that means then only our cache has the LFS object and not our permanent storage backend. So this might be a silent problem for a while until the object gets flushed from the cache. And oh crap, now we can't download the objects that we need. So yeah, so a naive solution would be to buffer the entire upload, wait for the success from S3, and save to disk. But yuck, that's disgusting. We can do better. This is Rust. So the best solution would be to stream to both and only commit to disk when the S3 upload is successful. And doing this with futures in Rust was a little bit unintuitive. So let me show you the solution for that I came up with. So here we split the stream. So this is the byte stream coming in. Say this is an upload. So this is a stream of byte chunks. So splitting just means we've got two streams, but they both refer to the same bytes. So if you call next on A and next on B, it's going to be the same bytes. So, and then we create a one-shot channel, and we use this to coordinate between S3 and the disk cache streams. And we recreate we upload to S3, but so put returns a future of a result. And so when that future succeeds, we want to send a message through this channel here. And likewise for the disk side, since B is a stream, we want to chain an additional future to the end of it. And so we take the receiver end of the one-shot channel and basically map that. So this is a future. Receiver is a future. We map that to an empty chunk of bytes. So basically, we put an empty chunk of bytes at the end of the stream, whose only job is to wait for the upload to succeed on the permanent storage S3 backend. So I thought that was rather clever. It solves the problem pretty nicely and still allows us to stream the bytes through. And so here's B. We put that to the cache. And the cool thing is, we do both of these operations concurrently using a future join, and we await the result. So the cool thing about this is it handles cancellation pretty nicely. In Rust, cancellation of futures is pretty nice. So say the client cancels their, like they press Control-C in the command line and they stop uploading an object. So that will basically cause the server to realize that the client hung up on them, and all of this, the client request will be dropped. So drop in Rust is basically the destructor in C++. And when a future is dropped, everything's canceled. So all this stuff gets deallocated and thrown away. So we don't ever have the case where we might accidentally fully finish the caching of the object without fully finishing the S3 upload either. I have no idea how I do this in C++. So there's another issue here too. We want to verify the SHA-256 of uploads and downloads. It's pretty simple on the upload part. We just, as we get the bytes from the user, we hash it. We basically, as the data is streaming in, we hash it and accumulate this hash. And if it's wrong, we tell the user to go someplace else. And the second issue is, what do we do on downloads? When we get an object and the SHA-256 doesn't match, that's a problem, because that means we have a corrupted object in either our permanent storage backend or the disk cache. If it's in the permanent storage backend, there's not much we can do. We've had data loss. All we can do is restore from backups. If it's in the cache, we can actually do something smart and delete that object from the cache. So yeah, so here's how we handle it. So yeah, I think I mentioned this already. So we can write a wrapper for the byte stream, which basically computes our hash for us. And if the hash doesn't match, an error is returned. And so on the final chunk from the server, as we're downloading this thing, we know the length ahead of time, so we know when we're going to see the final chunk of data. And once we've got the whole object, we can verify that SHA-256 is correct or not. And if it's not, we never send the final chunk to the client, the final chunk of bytes. So the client will, actually, I'm not sure what the client will do in that case. I think it'll just retry. Oops. So yeah, so if the hash is wrong, we just spawn a background job using Tokyo spawn, and that'll delete the object from the cache. And so next time the user tries to get the same object, maybe the cache was corrupted, but the permanent storage backend was not. So next time they hit our service, the cache will say, "Oh, I don't have the object. I'll get it from S3." And it'll get cached correctly next time. So in conclusion, if you have questions, please start typing them out. Some of the challenges I had were using Futures 0.1. It's rather cumbersome. We didn't have the await, async await syntax back then, so we didn't have all the nice syntax sugar. I eventually switched it to async await a couple of years later after it stabilized in Rust. Yeah, and just figuring out how to cache uploads and downloads correctly just took some time. And it took a while to realize that S3 actually throttles your requests. This was an issue I only saw when uploading many gigabytes of data at once to S3. I'm like, what the heck is happening? Turns out S3 will throttle your requests and you should retry. That wasn't built into the Risotto API that I was using. There's some nice libraries for this. It's pretty ergonomic to implement a exponential backoff strategy with futures in Rust. Error handling is always difficult, but Rust really forces you to do that correctly. Kind of puts errors out front and center, whereas I guess I can bash C++ a little bit. C++, you just throw an exception, and who knows if anybody catches it or not. Another thing I probably wouldn't do is use Hyper. Hyper is a rather low-level library for dealing with, for making a REST API. Back then, the web app framework stuff wasn't very mature. So nowadays there is libraries like Warp and Tide that would be much better to use. They implement the nice handling and routes and stuff. I had to do all that manually. And so results, Rudolph's is probably the fastest Git LFS server out there, as far as I know. Last time I tested it, it was about twice as fast as Artifactory or Nexus, probably just by virtue of not being Java. Even faster, even though it's doing encryption. These don't do any encryption at all. So it's pretty stable and reliable. As far as I know, nothing's gone wrong. Maybe somebody can correct me who still works at Esri. It's got a super tiny Docker image. It's 4.5 megabytes. Rust makes it pretty easy to compile with muscle libc, which is a statically linked libc. So you can cut out a lot of so you have like one small static binary, and that's it. You don't need the rest of the operating system. And I'll just leave you with this quote for those who need to convince their team to learn Rust. It's probably easier to learn Rust the first time than it is to learn C++ the second time. It's something one of my colleagues said. Thank you. If you have any questions, I'm happy to take them.
That was awesome. Not seeing questions in the chat right now, but I'm sure people might have questions in their minds. Does anyone have any immediately? You can feel free to unmute yourself.
Jason, you did mention that something about those results or options within results. Can you once again explain why you needed that nesting?
Sure. Let me go back to that slide. Oh, there we go. So yes, result. So I for brevity, I left off the second template parameter for the result. There should be a comma plus an error type here. So a result is basically in Rust. It's like the de facto way of handling errors because there are no exceptions in Rust. Well, there are, but they usually crash your program because it's some user error. But I mean, programmer error. So for result, it's either okay or an error. So this something C++ doesn't have is forget the name where enums you can have a type associated with your enum. So and an option is pretty similar to a result, except that it's something or nothing. It doesn't have the error type. So in this case, when I do a get on this key, the request might succeed, but I might want to say this object doesn't exist. So this would return okay, none. I hope that answers your question.
Mm-hmm. So wouldn't it be better, for instance, to just have an enum of those three types?
No, because for result, there's some nice syntax ergonomics where you can put a question mark operator and then propagate the error type to the caller. If you were to combine all these into one enum, you can't really do that.
Got a question in the chat as well from Richard. How long did it take you to learn enough Rust to be able to write this?
Oh, well, I've been using Rust since 1.0, so that's been about 6 years now. So yeah, I would say it took a while. The features, the aspect of using features like this took quite a bit of time to learn. I think it was totally worth it though. So if I were to put a number on it, I would say 6 months to a year, you can get to this point easily.
Does anyone else have any more questions?
So when you were implementing this server, right? Did you take any into consideration options for like exhausting resources, or you just assumed, okay, at this point it would be just viable to crash?
Resources like CPU resources, or
so even the
memory.
memory resources, if you have too many requests going on at the same time, and then basically, what is the approach to it? Or is it just a beefy machine? And
Yes, the approach
maybe
is
starting it from time to time.
yeah, the approach is to give it a beefy machine and hope that never happens. The better approach would be to use something like Kubernetes to make sure you have some failover. So with this design, since it's really just a caching mechanism for S3, you can actually stand up multiple servers like this and use some load balancing to make sure something always exists for you to hit.
I have a question. Do you use this now, like yourself in personal projects?
No, I don't. I have no need for it. I don't work on any projects that would benefit from storing large files anymore.
Oh, and we've got another question. Oh, a couple of questions. Futures is hard in any language. Do you think it was harder in Rust?
I've never actually used futures in any other language. I came from a C++ background. I've dabbled in C# a little bit, but I never really used async await in there that much. I would say it's probably a little bit harder in Rust than it is in C#. But I can't really tell you.
Okay, another question from Peter. Jason, why did you use pin for type byte stream equals pin box dynamic stream? Does stream act as unsafe or foreign data?
I was hoping nobody would ask that. So pin is a rather complicated concept. Basically, it's just a marker type. It adds no extra bytes to your type. So pin just says this type should not move memory locations. It's an optimization for futures, and it's also there to ensure correctness. So yeah, there are reasons to use pin. I also left off some other marker traits here, like the stream should be sending sync, and it should have the static lifetime, but I left that off because it wouldn't fit in this slide.
So did you have any concern about access control?
Yes. Well, not internally, because it's one company, so it's fine, and it's hosted internally. So, and they're all assets. It's not code, so it's not particularly important intellectual property. So I would say the code is more important to control access to. But if I were hosting this externally, yeah, I think should definitely have some access control. Probably based on a namespace or something. Access control is hard to implement, so I didn't do that.
So just last question from me. Did you also consider maybe not encrypting files that were going to the disk if it was always inside on the intranet? Would it speed up things up?
It probably would, yeah. It definitely adds some overhead, but I would say the main bottleneck is usually the disk itself. CPU, I think, can stream. I think it can do the encryption and more than keep up with the disk. A lot of encryption algorithms like Xchacha 20 or some other ones will use SIMD to make it faster. So I think encryption is pretty fast nowadays. So I think there's no reason not to encrypt by default. That's what I would say.
And what about the secrets? So the last but one question that was, what about the secrets for encryption?
Yes, that's a great question. So you have to generate an encryption key, and you have to keep that secret. So yeah, so that should ideally that would be stored in some like secrets vault.
Mhm.
And then when you provision the server, you use the secrets vault API to grab this key. One downside is if that key ever changes, all your objects become just garbage, and nobody will be able to download anything. So yeah, I guess there are downsides to using encryption.
That's usually the problem with the encryption, right?
Yeah. Okay. There's no more questions. Thank you, everyone.
Very good presentation.
Yeah, thanks for coming, Jason. And then I'll post the link to the repo on the Meetup for anyone who wants to see it.
Okay, great. Thank you.
Cool. We had one extra comment rather than question, which is just more for the S3 backend would be the encryption would be particularly useful.
Right. Yeah.
Do you know of anyone else using Rudolph's? Have you had many bug reports externally, not from Esri?
Not too many bug reports, mostly feature requests. I like to think that's because there are no bugs, but I'm sure there are bugs. I don't know of any companies other than Esri specifically using this, but they wouldn't come out and tell me anyway if they were. That's not sure.
Cool. Krzysztof, was there anything that you wanted to share now, or did you want to save it for another talk? I don't want to put you on the spot, but
yeah, I don't know. No. Yeah. Yeah, I'm not sure really. Maybe someone has questions, and then I could show things.
I know there were.
Yeah, I guess I just didn't plan the presentation appropriately for the time. I thought, oh, it's so much time. I'm gonna be fine with presenting all of it, but I should probably skip that introduction and then how the file format looks like and stuff, and just go to the project.
There were a couple of questions in the chat. Someone asked, regarding security, is there any permissions model similar to iPhone and Android applications with some digital signature security in WASM?
I don't think so. At least not from what I've seen, right? I guess the runtime is allowed to do whatever it wants, right? So if it was to check signatures or check whatever before even running or before even compiling the code, it would be free to do so, right? Like even with that JavaScript API I showed, you're in charge of fetching the content, converting it to the byte array, and then instantiating it. So before doing that, you can have a check against the certificates and making sure that someone you trust signed this, and then the signature agrees with what you would expecting. So it's not like out of a box, but definitely you can add yourself to it.
I read another question from David. If Emscripten was designed for porting the existing native programs to WASM, is there a newer tool for compiling new programs to WASM?
So I sent back the direct message, but isn't it showing up? I thought it's just like adding David. But anyway, so the thing is, Emscripten is just it's not the tool that is designed for porting, right? It's the tool that is designed to be easy to use, and by that, it's also easy to port. So what they did basically is that in WASM, you don't have your operating system. So you wouldn't be really able to use anything operating system specific. So you wouldn't be able to use file system. You wouldn't be able to use anything that is using system calls, right? But they did recompile the libc module, and then whatever calls, external calls are being made, then they have their glue code, sometimes implemented in JavaScript, that is basically making it working in the browser. And it's not for porting, it's really for making your coding in C++ natural, I would say. And it's for the browser, right? Then there is also like WASM can be run in other environments, and some of the environments they will be supporting WASM, which is like a WebAssembly system interface. And with such a thing, you don't even have to do any of that glue code, right? Because they are basically trying to be, so the WASI is trying to mimic the POSIX interface. But I wouldn't say like I did like working with mscripten. Obviously, I don't have an experience with anything else, right? And mscripten is also like so. On that simple project, I've been using just simple types, and that's kind of because WebAssembly only allows for communicating with the integers and that memory, right? But and then you have to do that serialization and deserialization yourself. Then mscripten is also like encompassing bingen, and web IDL. So you can, with some particular higher level language, you can say how map your C++ types, for instance, if you wanted to pass more complicated structures between those two languages. But it's all really serialization and the deserialization on the other side. And then WASM, I think now they have a preview of the specification for interface types or something like it, right? And then you would be able to use more complicated types in WASI. But again, the way how they're going to be implemented, as far as I'm concerned, is by serializing and deserializing. So you could use, for instance, protocol buffers even for doing it, right? But those are designed, those protocols are designed for serializing and then sending over the network, for instance, if you're not sharing the memory. Whereas those interface types, they're designed to exist in the same memory space. So they should be more performant. And some people think that after getting those interface types, you basically so the whole WASM ecosystem is going to be awesome, and then you will be able to easily talk between Rust, C++, other languages, and you could just write your microservices code in the same really process, right? We'll see how it goes. But coming back to mscripten, so you can just use Clang, or I'm not sure if GCC, for instance, is supporting WASM target, right? But it's just a tool that really helps in getting your code running. And yeah, you don't have lots of the boilerplate. I said lots of words, but not sure if that made sense.
Conclusion: mscripten good in your.
I think so, right? So yeah, this is like, so the mscripten is something I think by people on the committee for WebAssembly, and then they're using it to try out different things. So this is like the most prevalent tool, right? And usually it also has many features implemented as it goes into the standards and so on. I'm not really aware right now of the other tools that you would be able to use.
Awesome. Does anyone else have any questions? I think not, in which case that's probably a good place to wrap up. If anyone who is here wants to do a talk at any future meetups, then yeah, please get in touch. And yeah, I'll post a link to both your GitHub, Krzysztof, and Jason's in the chat. And this was recorded, so I'll try and get this uploaded in the next couple of days and post a link out. So if there are any particular bits people want to look back over and be like, how the hell did that work? Then they can. And yeah, we'll try and get these meetups happening more frequently. So maybe within the next 6 to 8 weeks, I think we'll probably be being realistic. That'll be the time frame. And yeah, happy St. David's Day, everyone. Thanks everyone for coming.
Thank you very much, guys.
Thanks. See ya.
All right.
Thanks, guys. Thanks for that.
Bye, everyone.